Yes.
Is it okay if we have our own graph paper that we use?
Yeah. I just posted the graph paper to be convenient.
Okay.
Okay. Use whatever you like. I'd like the graphs to be made carefully.
Yeah.
But yeah, I just posted it so you wouldn't have to go out and buy some if you didn't want to.
Okay, thank you.
Okay, so today it's going to be on functions and relations. And one of the things that you'll find as you go through calculus is that functions are going to become increasingly more important. There's oftentimes kind of this blur of what's a function and what's just an equation. And so what I want to do is establish formally what a function is, and then we'll look at how we can tell if something's a function, and then go on to piecewise functions and graphing functions and things of that sort. So first we start with a relation. And a relation is just some ordered pair, a set of ordered pairs. And this can be discrete numbers like what we have here, or it can be like a rule that you apply algebraically. So if you get one number, you can get the other number. So here I'm just going to use these ordered pairs. So the set of the first numbers is called the domain. Okay, domain is a set. There's nothing really that tricky or fancy about it. And then the set of the second numbers, the components, it's called the range. And so in this case we have 2, 3, and 6 as being the range. So one of the things that you'll notice about this is that the elements of a set are just listed once. All right, imagine you're in a grocery store and you're going to look at certain products and prices. That if you look at, let's say, a can of tomato soup, it has a certain price. And then if you go to different aisle and you find, let's say, a loaf of bread, it has a price. Or you'll find maybe different variations of the same product, and they'll all have maybe the same price. When somebody asks you what's the range of prices you saw, you can say, well, I saw something that was 99 cents, $1.75, and two things at $5. So when you're naming a set, you don't even have to say how many of those elements that are in the set. It's just that a price of $5 is a price of $5. So it may be associated with more than one product. Same thing here. You can have the 6 is associated or related to both the 5 and the 0, but we don't have to call out the 6 separately when we're constructing sets. So a set is just basically identifying, what are the possible values of the domain and the range, not, how many times do they occur. Okay, so that's a relation. A function now is a rule. It takes each element in the domain and it assigns exactly one element in the range to it. So if we go back to the grocery store, we have a relation between the product and the price. The product, the set of all products is the domain, the set of all prices is the range. Now, you would hope that a grocery store would price its products using a function, not just an ordinary relation. And the reason why I say that is when you bring an item to the checkout, you're going to expect one and only one price for that, right? You bring a can of soup to the front, and they'll say, well, that's $1.50. They will never say it's $1.50 or $2.25. I mean, that doesn't really make sense, does it? So that's kind of the essence of what a function is, that anything that we have in the domain has exactly one thing assigned to it in the range. Okay, so it's possible, just like with that pricing analogy, that the range, that the different values in the domain can be assigned the same value in the range, but it's exactly one assignment that's being made. Okay, so let's say we have, look at it this way. If we have a domain and a range, you can look at a function as a mapping as well as a rule that says, okay, when I say 0, you say 4. When I say 7, you say 3. So the input would be 7, the output would be 3. Like I said earlier with the, so we could call this a function. All right, this one. Like I said earlier with the grocery store prices, we can perhaps assign more than one thing a price, but if we have an item that has 2 prices, like the 7 is associated with both the 3 and the 12, it's not a function because 7 is associated with two values, 3 and 12. Okay, so that's the real essence of a function is you get one answer out of it. It's just like your calculator. It's a 4-function calculator. You put an operation in, you only get one answer. Okay. So if we look at a different case where in a domain we have both 0 and 4 assigned to a 1, or you get a 1 out of a 0 or 4, this is a function because there's only one number associated with 0 and only one number associated with 4. It's okay that the range is that an element in the range is used more than once. Okay, so let's talk about how we write functions and function notation. You've seen this perhaps before, this f at x concept. This is a little different and perhaps ambiguous kind of notation, because if f was a variable, you could think of this as f times x, but with functions this is not the case. With functions, we're going to call f the name of the function. It's not a variable, it's the name of the function. And x in here is the value from the domain that the function operates on. Okay, so go through some semantics here. So the function in this example is f, and then the value of f evaluated at x is f at x. Okay, so think about this as a subtle difference. F at x we think of as a function. Well, it's the value of the function evaluated at x. F is the function. Now, you'll hear me say this 2 different ways. You can say f of x and f at x. And I think f at x is the probably the more common. I'm not entirely sure. It means the same thing. It just doesn't mean f times x. It means f evaluated at x, if you want to look at kind of the long way to say that. And so while we have up here f is the name, f at x is a value. Okay, so what you're saying is that this function applies a rule to that variable x to get another value. All right, some more notation here, or maybe a couple examples. So let's have this function, and I'm defining it as f at x equals 2x plus 1. Now I put the whole f at x because I'm declaring there that x is the value that I'm going to take from the domain, and what I'm going to do with that then is I'm going to multiply by 2 and add 1. Okay, so this is about as simple as a function as we can find. So when we evaluate the function f at 0, we put 0 in where the function is. Now, I think I've mentioned something like this before when we were calculating slopes. I think one of the easiest ways to do this, now this one you can do in your head. This is really, really easy. But one of the ways that you can do this with more complex functions and things is write your function, the rule, with parentheses instead of the variable, and then drop that value of the variable right in the equation, and then you evaluate it. 2 times 0 is 0, plus 1 is 1. So take another value, and where you have negative numbers, this is where this really is a beneficial kind of way to do things. I still write my rule, and then I drop the -3 in, and so I can evaluate that as -5, because 2 times -3 is -6 plus 1 is -5. So especially when you have functions that have a lot of different signs in it, if you're trying to evaluate values that are negative or maybe are an expression rather than that, this method of first writing out the function then dropping it in there really doesn't cost you any more time, but it keeps you really in order in terms of not forgetting to do a double negative if you get an expression with a negative. So now it's possible that I can put another variable or perhaps an expression like x plus 1 or anything like that and evaluate my function. And so whatever that expression is, I put it in there and then I can simplify it. So if f at x equals 2x plus 1, then f at t equals 2t plus 1. Okay, so let's look at a little bit more complex function. This thing is 2x squared minus x plus 1. If we evaluate that at 1, I write my equation, or write my rule with parentheses, and then wherever I have the parentheses, I'll drop in my value, and then I do the arithmetic of 2 times 1 is 2 minus 1 plus 1, and I get 2 out of that. Okay, and here you can see hopefully the value of writing it this way, where I just write my function and then drop in the -2, and you can see here I'm saving myself from a potential error if I don't remember or kind of get confused and don't make this double negative right. Here it's written down, so it's easier to keep track of, so we can just write 2 times 4 plus 2 plus 1, so we get 11. So it's just a matter of having this thing that you drop values into to get other values. Okay, so let's look at at another function. F at 0, again, do the same thing. Write it with a parentheses, put a 0 in there, we get -1. We simplify it. If I take -2, I'll do the same thing. I write my function, drop in the -2, and then that computes to 1 over -3, which is the same thing as -1/3. Okay, so here's a little twist. What is f at 1? So if I try and evaluate it, I get 1 over 0. So what does this mean? It's undefined. Okay, and what is the consequence of this being not defined? I'm sorry? One of you at a time. Okay, try again.
It's not a solution.
It's not a solution. It's not really a solution. It's not a value of the function. It means that 1 is not in the domain of the function. Okay, with a solution we're trying to find a value for x that makes it true. Okay, but we can put in any value for x that we want because it's a function. We can't, though, put in 1 because it doesn't have any value. It's 1 over 0, not defined. So we say that 1 is not in the domain of this function. So if I look at these earlier functions, I can put any real number in here and not get in any trouble, right? So the domain of this function is all real numbers. Same thing here. With a polynomial, I can put in any number, big or small, negative or positive. Nothing happens to it. I just get a number, so I say the domain here is all real numbers. But here, there's one particular value that doesn't work, so I have to exclude that from the domain. And so it's undefined, and we say that 1 is not in the domain. Okay. So we have a function, and we can have what's called an implied domain. And an implied domain is a domain that you can tell by looking at or analyzing the functions what numbers work, that you don't have to actually say, what the domain is. Now, if we have an implied function, an implied domain in this one, we notice by inspection all numbers work, and so we can say the domain is all real numbers, or we can use this funny looking R, which is kind of a capital but not quite bolded R, or we can write it in interval notation as negative infinity to infinity. Okay, so we have a couple ways to write it there. In this one, we found that 1 is not in the domain, so we would just write it in plain English like that. We can write it as the union of two intervals. Okay, you've had some practice doing this, where we're saying, okay, you can go from negative infinity up to but not including 1, and then you could start again but not include 1 and go all the way up to infinity. And so this is kind of a long way to express the fact that you're just trying to eliminate one value, right? I mean, that you'd have to kind of read that more than just glance at it. So there's a different way, and it's called set builder notation. And set builder notation, we're going to use these braces on the side to enclose our set. And if we just list values in there, that would be a perfectly good way to write a set. But this one has a meaning. I'm going too far here. You read this as the set of x such that x does not equal 1. And so what we're implying here is that all other real numbers work. All right? So we're not dealing with complex or imaginary numbers in this course at all, so we're just going to consider real numbers. If I put an exclusion in here where x cannot equal 1, I'm going to assume everything else works. Okay, so here's a function now. Notice that we can only take the square root of 0 or a positive number. We can't take a square root of a negative number without getting into imaginary numbers. So in other words, this expression that's on the inside here, this x minus 1, that has to be greater than or equal to 0. All right, so then if I just solve that, add 1 to both sides, x is greater than or equal to 1. Now this is our domain, right? Because any value that's greater than or equal to 1 works. If I put in 1/2, that's not going to work because I get 1/2 minus 1 is negative 1/2. 0 doesn't work because 0 minus 1 is negative 1. But any number that's 1 or more works. And so we say our domain is starting at 1, including 1, all the way up to infinity. Or when we're using set builder notation, we just basically write the same kind of beginning, the set of x such that x is greater than or equal to 1. So this reads just like you would say it. Maybe you don't use the phrase such that, but I hope you understand what that means. That's that vertical line. Okay, so not worrying about domain notation too much. Let's just think about this one. What's the domain of this function? Okay, what if I put in a number, I'll get another number except in one case. And what's that one case that I don't get a number out of it? It was 3, right? So the way we do this is that when you have this, maybe I even wrote it this way. So we say all real numbers such that x is not equal to 3. So when we have this thing, and we have some expression, I'll call that a, divided by some b. So we have some ratio like this. The way we determine our domain restrictions is that we set b equal to 0 and see where it equals 0. So in this case it's 3 minus x equals 0, and so we solve for it, x equals 3. So that's one that you could probably do in your head. But if you have a little bit more complicated expression, like you're trying to find a 0 of a polynomial or something like that, this is the general way that you do it. Okay, everybody up with me on the notes? Okay, so let's get back into this notation thing where we're notating a domain as a set. So you can write, if all numbers work, you can just write this R. And you don't need to put it in braces, because then if you put it in braces, that'll mean the set of real numbers, and that's redundant. It's the set of real numbers. You can put it in intervals, and you can use the set builder notation. So just to break this down a little bit more, that when you open the brace there, that means the set of. Okay, so that's just, you're scanning along, and that is the signpost that says, here comes a set. Okay, so the set of, and then you just declare a variable right here, and then you have this vertical line, and that means such that. Now you often see this in other textbooks as a colon, so you might see it like this, where you have a colon instead of the vertical line. Either of them is fine. They're both pretty widely used. They're both on the keyboard. In fact, the vertical line is the uppercase backslash. That's the last key on the second line if you're typing. And then you put whatever expression you want after that. X is greater than or equal to 0. Okay, so what I'd like you to do is try writing the domain of this function in set builder notation. So there's two things you have to do. First, you have to figure out what is the domain of this function, and then the second thing is, how do I notate that with set builder notation? So you go to the movies, you walk up to a window, and you see this table up there, and everybody understands the price structure of it, right? So let's talk about this in terms of domain and range and a function. When you go to the movies, you go up to the ticket counter, you say what your age is, and then they give you exactly one price. So then the price would be a function of age, right? If the age would be the domain of the function, the range of the function would be its price. The input is the domain, the output is the function. So we have actually three rules here. We have, if you're under 14, you pay $5. If you're between 14 and 65, you pay 15. And then if you're over 65, you pay 10. Okay, so we have the domain, which is the age, is broken up into three different segments, so to speak. So what this is actually what's called a piecewise function. So you don't have a single rule that defines the function. The function is defined in pieces according to different pieces of the domain. So in this case, let's call A the age. So I'm defining my age as being A, that's the variable I'm going to use. And so what's the domain of A? Well, the domain of A, if I look at the table, well, -2 works in there, but that's not a practical age, right? Nobody is 2. People are 0, and they get, presumably, 100, 110, or whatever the maximum practical lifetime is now. We don't set an upper bound on it, but we do put a lower bound on it. The domain is a positive number. Okay. So if we look at the parts of the domain, we have three different parts. And I can write this instead of my table on the movies here. I'm going to define that as three different parts. So one part is less than 14, another part is between 14 and 65, another part is when it's greater than 65. And so I want my cost of admissions to be C at A. So there's my function. All right, so I've decided on the name of my function, and what C at A means, that's going to be the price, and I have parts of my domain. So now what I do is I'm going to write it in this fashion. So I'm going to say my function is either 5, 15, or 10, depending on what part of the domain I'm in. Now oftentimes you'll see the word if in between these two. It's 5 if A is less than 14. You can think of it that way. Or when, sometimes you see that, 5 that your function is 5 when a is less than 14. But in order to look up the price, you do just the same thing as you do when you go up to the window. You see, okay, what's my age? What's the cost? So math being unnecessarily complicated, they do things backwards, right? Where you put the rule for the domain as the second part, and you actually have the function as this part that's closer to the C at A part. Okay, so piecewise functions can be, they look more complicated than they really are. This is just basically a way of defining this exact table using our function notation. Okay, so we have part of the domain and the value of the function. Now, it doesn't have to be a rule like just a 5 or a 15 or a 10, a constant. We can have expressions too. Like, probably nobody would go to this theater, but if the rule for when you're between 14 and 65 is you're going to pay $1 more than your age, okay, that's quickly becomes very expensive to go to the movies, then you would just put a plus 1 right here. Okay, so that means you take your age when you're between those ages and you add 1 to it. That would still keep the price under 14 at 5 and the price over 65 for people over 65 at $10. So instead of numbers here, we can put expressions, and most of the time that's what we're going to do with piecewise functions. All right, so let's revisit absolute value, and let's define it as a piecewise function now. So you all know what the absolute value does, right? We put a number in the absolute value, and it gives us the positive version of that number. So the absolute value of -5 is 5. Absolute value of 5 is just 5 unchanged. So let's make that a piecewise function. So f at x, and then our standard notation for the absolute value. The function can be defined like this. So when we're negative, when we're less than 0, we're going to take the opposite of that, or the negative, to make that positive. If x is greater than 0, we're just going to leave x alone. So this is the output value of our function, and then this is the rule. These two are the rules of for what part of the domain you're dealing with. Okay, so if we take f at -2, okay, which one corresponds to, and this should be, I think, a -2, maybe, I wrote in a -2 there. Okay, so which one of these corresponds to -2? Well, x is less than 2, no, x is less than 0, -2 is less than 0, so this is the definition of the function that we're using. And so when we use that part of the function, we say f at -2 is -2, which is +2. Okay, so maybe that seems more complicated than it really needs to be, but the point is to illustrate a piecewise function that's defined, that gives a definition to absolute value. So we simply write absolute value of -2 is 2, which you knew before this. Okay, so here I have a piecewise function, and I think what I did here was, this actually here should be f at x. I wrote g, so either this has to be g, and all of these are g, and I think I make a correction a little bit later, but let's first examine this. If we take 0, 0 is in what part of this, between these two pieces of the domain? Well, the 0 is less than 4, so we're going to use this definition of the function. So we'll take 2 times 0 plus 3 is 3. Now, f at 7, there, you see I made my correction here. It's actually f at x, okay? So f at 7, which part of the domain applies to it? It's going to be this. This is x is greater than or equal to 4. That's true, 7 is greater than 4, so we're going to use this as the value of our function. And so we get 7 minus 5 equals 2. Now if we try 4, we look at these, and notice that one of them is an inequality, and the other one is the inequality with an equal sign. You can't have these pieces overlap, because then what you'll do is you'll violate the value of the function, or you'll violate the definition of a function where we would have two possible values for our function. But you see, only one of them includes the equal sign. So when we take f at 4, we're looking at the second row as being the value of our function. So we plug in the 4 minus 5 is negative 1. Okay, any questions about piecewise functions? Let's talk about graphs of functions. I've talked about graphs several times, about graphing lines, graphing points on a line. So let's talk about graphing in terms of a function. A lot of this is the same that we've had before. So if we define a function, here we have a list of possible values or representative values from the domain. And so here is the output of the function, the range. This is not that different from when we said y equals 2x plus 1. And so we're going to get a graph that looks just like we've had before, where it's just a line. If we do the absolute value and we put in the function, we're going to get something that looks like this, okay, where it's going to be a straight line on both sides of the 0, but it changes direction right when we hit 0 because that piecewise function actually changed when we got x is less than 0. So let's have a piecewise function here that combines these two. So I'm going to make this thing, when x is less than 0, I'm going to make this negative x. And when x is greater than 0, I'm going to make it 2x plus 1. All right, so I do the same thing, make up my table, and then I make up a graph. Now the graph is going to look a little different. It's going to be disconnected. You can see right down here. So this part of the graph here, or I guess talk about the left side first, this part of the graph, when x is greater than 0, it's going to be this line. And so it ends where x equals 0, okay? Because that's our rule that says that the function ends, or this definition of the function ends when x equals 0. And then for the other values, we're actually going to take negative x, so it's going to look kind of like the left-hand side of the absolute value function. Now, here's a real danger in plotting functions with just these points. Think about what would happen if I'm graphing this thing manually. And so I have at negative 3 and 3, I'm going to have 1, 2, 3. I'm going to have this point. At negative 2, I'm going to have 2. I'm going to have this point. Negative 1, I'm going to have 1. And then at 0, since I'm going to the other definition, I'm at 1. And then at 1, I'm going to be at 3. And 2, I'm going to be up at 5. So I'm going to be up here. Now, you have to be really, really careful that you extend the definition of this side all the way to the axes, that this does not go over, in a straight line and go up like this. You have to recognize that your domain of, in that first line goes all the way, but not including 0. So what we do is you put an open dot where it ends, but it's never going to be equal to that. So if we put in a 0 in that first one, negative 0 is 0, here we get our line that looks like this. And so then we start worrying about what's on this side. The first point there is when x is 0, and so you have this thing going off like this. So you have these discontinuities. So make sure when you're dealing with piecewise functions that sometimes they'll connect, sometimes they won't, but make sure you get the behavior of it right by looking at what is it when it's near where they're switching values, that you get this and not this. Okay, that would be the temptation if you're just looking at points. Now, one of the things that is going to be helpful to you in calculus is having kind of a toolkit of basic functions where you know that these are going to be the simplest functions, and you'll know what they look like, you know how they behave, and that other functions will be built from these. And so we'll deal with that a little bit today. So, of course, the ultimate in simplicity for a function is that the function has one value and only one value. So no matter what x is, we get one value. And so that's a straight horizontal line. F at x equals 3. If we take a function like the square root always gives us a number that is positive, and it starts to curl over like this. It's kind of this parabola on the side business, but it's not defined in any of the other quadrants. It's just in this particular quadrant where x is positive, and it only gives you a positive number. So the square root of 9 is not plus or minus 3. The square root of 9 is 3. Okay, we'll talk about where we get the plus or minus a little bit later in the semester. Okay, so another basic function is just if f at x equals x. Another one is the parabola f at x equals x squared. And then the absolute value function and x cubed. So notice I didn't put too much of a scale on these things. I think it's important for you to, when you see these functions, to recognize what they what conceptually they do graphically. Now, oftentimes you'll be asked, or you'll have to decide, does a function behave a certain way? And so one of the things or does something hold true for all functions, or things of that sort? One of the things that you do is then go through your list of these kind of basic functions, and you say, well, is that true for f at x? Like, one of the issues is going to be, is a continuous function always differentiable? Now, I don't expect you to really know that, but in Math 13, you're going to get to that. And they're going to talk about continuity, they're going to talk about differentiability. So when you have a question like that, think of these functions. Is it true for this function? Is it false for this function? And all that. So this is kind of building a toolkit for you to think about when you're studying calculus. Okay, so let's talk about the vertical line test and what this is for.
What was the equation for the parabola?
Okay, and then yeah, you got the cube and okay, good. Everybody okay? Everybody up? All right, so let's talk about the vertical line test. Perhaps you know what the vertical line test is, but it is a test that answers the question, when you look at a graph, is this thing a function or not? Now, it is basically a way to graphically determine, does the function only have one value for every value in its domain. So let's say we have this kind of graph, and we're looking, is this thing a function? So you can kind of work through it by looking at this from the standpoint of, if I take any value along here at x, I'm only going to get one value. And I can look down here at this value of x, I'm only going to get this one value. And so notice there's this kind of vertical look at it. For any value of x, do you just get one? Okay, contrast that with a graph like this. This is a perfectly good relation. Okay, so there's ordered pairs that you can place on there and call them out. But if I'm over here, if x equals some positive number, well, there's two y values that correspond to it. So if I imagine a vertical line here, the vertical line will go through the graph twice, but here, which is a function, it'll only go through it once. And so that's what we mean by the vertical line test. Just imagine this vertical line, sweep it back and forth. If it crosses the graph at most one place, it doesn't even have to cross the graph. Like you can have a function that ends, and so you have values that the function doesn't exist. That's okay. That doesn't disqualify it from being a function. But it must pass the vertical line test. Wherever we have a vertical line, it can't pass through the curve more than once. Okay, so this second function, the vertical line here, it fails.
So it's not a function?
This is not a function.
So anything where it's x squared is not going to be a function?
X squared is a function, though. This is not x squared, that's y squared. Okay? Or y squared looks like that. I didn't actually plot y squared. Okay, so let's look back now at our elementary functions. Every one of these passes the vertical line test. So it's just a quick visual way to do it, to decide if it's a function or not. Okay, so let's look at graphs. Now, here are three functions. And they all involve an absolute value. And so you would expect that there's some sort of similarity between these functions. Now, we do different things to it. On the second one, we subtract 2 from x before we take the absolute value. On the next one, we first take the absolute value and then add 2. Okay, so if I'm going to make up some values, we'll do this the point way. And I understand this is a lot of writing to write, so you can write some representative values and check with my notes in a little bit. You'll see that we come out with different numbers, but if I put it on a graph, there's f at x, and then g at x looks just like f at x, only it moves over 2 spots. Okay, so it shifts the whole graph over. And so if I look at the relationship between f at x and g at x isn't 2 more. Like here's a case where f at x and g at x are equal. So it's hard to see out of these values what's really going on, but visually you can see this thing has shifted over 2. Okay, so now let me make a graph of, or put the, this thing has shifted over 2. Now, if we look at h at x, now, I don't know if you caught that, but we have a double line here. So h at x comes down here, and then it turns right around at 2, and then goes up. And so this one, you can see that from f at x, it just literally adds 2 to every value. And so this one's a little easier to see on the table what it's doing, but graphically when we add a constant to a function, we're moving it up, or if we're subtracting something, we're moving it down. So when we make these kinds of changes, we're talking about a translation, where we're moving this graph, and we can do this with any of our basic graphs, and we can get new graphs out of it. So when you see a parabola that's not right on going through the origin or so, then we can understand that there's been a translation that has occurred. So that's up to. Now, I say translations. Translations moves it about. Transformations may multiply it. So you may widen something, stretch it, shrink it, things like that. So transformations is the overall. So if we take, probably that h at x was the easiest one to see where we just added something to it. If we just add a constant to a function, it's going to shift that function up by the amount that we add to it. So if we add, in that case before, if we added 2, it's going to shift it up 2. And of course, the reverse is true. If we subtract c, then we're going to get something that shifts down. Now, if before we do anything, if we take our value of x and add a constant to it, it's going to shift it. And it's going to shift it to the left if we're adding something, and it's going to shift it to the right if we subtract something. Remember on the last one where I had the absolute value of x minus 2, it shifted it to the right. Okay, so you have to remember that the negative moves it to the right. Almost seems like it should be the other way around, you know, at maybe the first time you think about it. But if you really carefully think about what's happening, is that it is not only, you can look at it as moving the graph, but you can think of it as moving the axes. And so when we're subtracting 2, we're moving the axes to the left, and if we're adding 2, then we're moving the axis to the right. The graph then moves to the left with respect to the axis. So it's a couple different ways to think about it. Okay, so f at x, if I'm going to take h at x equals f at x minus 3 plus 2, this means I'm going to go right 3 units, and that means I'm going to go up 2. So I'm going to take, probably the easiest thing to think about is this vertex down here, and I'll move it right 3 and then up 2. You can see that my little vector there is where it moved, just up like that. And that's true for every point, not just the vertex, but every point goes through that translation. So we can keep the shape the same and just take, kind of like grabbing it by one point and moving the whole thing. Okay, so now let's talk about reflections. A reflection is when we take, let's say we have a graph. You're looking at a graph, and you hold it up to the light, and you turn it around, and you see essentially the mirror image of the graph. And that's what we're talking about with reflections. So we have, in this case, 3 possible ways that we can reflect this graph. Okay, so if you recall what the square root of x looks like, I'll make my my tables here. This does not exist. F at x does not exist for negative numbers, but it starts at 0, and I can make the table like this. For g at x, now since I'm taking the negative negative 9 becomes a positive 9, and so here I have values for g at x, but my domain has shifted. I can't take the square root of negative positive number, right? And then I'm going to look at h at x, and this is just the negative of f at x, so the domain still has the same thing where I can't take negative numbers, but I can change that on the outside from that column 1, 2, 3 over to negative 1, 2, 3. So let me make a graph and see if we can see what this is visually now. All right, so I'm going to plot first f at x. Now if I plot g at x, you can see it's just a mirror image. It just swung around that way. So when I first assign a negative to my x, before I do anything with the function, I'm making a mirror image of it about the x-axis. Now if I first do my function and then take the negative of it, then what I'm doing is I'm actually, well, yeah, a reflection about the y-axis. For h at x, what I'm doing is I'm reflecting it about the x-axis instead of the y-axis. Okay, so in general terms now, if I have a function and I make the x or the argument of the function negative, it's going to reflect about the y-axis. If I take a function and just take the negative of the function, I'm going to flip it about the x-axis. Okay, let you catch up on your notes there. So I'll cover this again on Monday. I'm going to show you one example. I think we still have time for you to try one of these. I know this gets a little confusing and is kind of a subtle thing, so it takes some practice. So that's why we're going to cover the same thing on 2 different days. Okay, so what I'd like you to try is describe what happens to this function when my basic function is f at x equals x squared. How does g at x look? What happens to f at x compared to g at x? What did you say?
It moves left and goes down 5. It moves left 4, goes down 5.
It moves left 4, goes down 5. Great. Okay? Everybody follow that? Because before I do my function, I'm adding 4 to it, so that means it's going to move to the left. And then after I do my function, I'm going to subtract 5 from it. That moves it down. So if I make my graph, oh, I guess this is a different problem. And we're going to work on this one on Monday, okay? Because we're going to practice a few more on the kind where we have a continuous function. But we can take any arbitrary function and we can move it around. And so on Monday you'll see that you're going to do that. So for those of you that came in a little bit late, we're going to have our test next Friday. That means Thursday's tutorial will be, you'll have some work to do there, but you'll also have a review in it. And there will be no quiz next week, all right? I'll get all your homework back to you on Monday, including the stuff that you're going to turn in today. So turn it in and have a good weekend.